Good evening, everyone. Welcome, welcome. We've got a full house tonight. This is really, really nice to see. Welcome to the December meeting of the Horological Society of New York. My name is Nicholas Manousis, and I'm very happy to see everyone here tonight. Before we get started, as usual, just a couple quick announcements. Let's get on with the show. New members and lapel pins. We had quite a few new members tonight. It was very nice to meet the new members who were at the first meeting. This is a nice first meeting to be at. If I did not get a chance to meet you, please come and see me after the meeting and I'll make sure to get you your lapel pin. We also have our archival history books up at the front and they're available for pickup on your way out, so be sure to check those out as well. So I wanted to speak briefly about the Henry B. Freed Scholarship. The Henry B. Freed Scholarship is given out once per year at our annual gala every April. It's a $5,000 scholarship to American watchmaking students who are either enrolled full-time or who have been accepted to a watchmaking school. And Henry B. Freed, who's Henry B. Freed? He was a past president of the Horological Society of New York and a prolific author on watchmaking. We have many of his books up in our library. So I'm very happy to announce that for 2018, we are expanding our scholarship program, and we're going to be offering 2 scholarships for next year. So 2 scholarships for $5,000 each. At our April gala, so we're looking forward to that. It's going to be a lot of fun. Is Justin Schellenberger here? Is he in the audience? Justin, would you stand up, please? Justin is the winner of the 2017 scholarship. Yes, Justin won that back in April at our 151st anniversary gala, and it's really nice to see you here tonight, Justin. And are there any other watchmaking students in the room? I know there are a few, some from Lidditz, some from the Patek School. Why don't you all stand up? Nice. So I want to give a message to the watchmaking students here tonight. Your work is important. You are tasked with bringing the art and science of watchmaking into the future. And I want you all to know that the Horological Society is going to be here for you on your journey. And we're looking forward to expanding and increasing our scholarship in the years to come. We're going to do everything we can to continue increasing that scholarship because we know it's so important to enable you guys to really focus on your studies and not really worry so much about paying the rent and other things while you're in school. And I also want to make it clear that the only reason we're able to expand our scholarship is because of the gracious support of our sponsors. You saw them in the first slide tonight, and you see them on our website and on all our emails. So please patronize our sponsors, and then also the gracious support of all of our members. If you're here tonight as a guest, welcome, and please consider joining as a member in the future. Your membership dues are reinvested right back into education, and they're very, very much appreciated. Okay, tonight's lecture. Tonight we're talking about the escapement. And the escapement has a very interesting history, right? To begin with, no one really knows who invented the first escapement or exactly when. But what we do know is that it's been contributed to and developed over the centuries by watch and clock makers all over the world. And tonight we're very lucky to have one of those watchmakers here with us. Our speaker for the evening, our guest, is the inventor of the single-wheel coaxial escapement, and he's the protege of Dr. George Daniels. Please join me in welcoming Roger W. Smith.
Well, good evening, ladies and gentlemen, and thank you for your very warm welcome. Thank you, Nick. And I must just say, yesterday I went and over to Brooklyn and was able to teach at one of the HSNY classes, and it was a brilliant afternoon for me. Wonderful initiative. And something that I think we're sort of sadly lacking over on the other side of the pond. But congratulations, you got an incredible president here and also team. There's Ed, there's Vincent, and something to really treasure. And I'm very envious of what's going on here in New York today. So my talk, I better get going, aren't I? Let me just get my things in order. So the title of my presentation to you this evening is The Development of a Practical Watch Escapement. Now, why did I simply not call it the development of a watch escapement? Well, it's because tonight I'm going to talk to you about what makes an escapement practical and the issues to look out for in the creation of a successful watch escapement. I have now been working with a coaxial for 20 years, and 12 of those years have been all about designing my watches to house this incredible escapement. What I have come to realise during this time is this: an energy-efficient escapement can have far-reaching consequences for the rest of the mechanism. As a result of my focused development of the coaxial, my service recommendations for my watches have increased from 5 years to 7 years. And today I'm recommending that the only time the watch should need servicing is when it stops. That could be in excess of 10 years, it could even be 20 years. At the moment I just don't know. But in any event, I'm happy that my movements will be long-term performers, thanks in great part to their escapement, but also due to a solid approach and understanding of practical watchmaking. And so how have I come to this conclusion? Well, over the next 40 minutes or so, I hope that this will all be explained. Just as a little footnote, I hope that you all managed to view George Daniels' 1990 lecture to the American Watchmakers and Clockmakers Institute. For those of you who did, great, but for those of you who did not, then no panic, because I will be covering many of the key technical aspects covered by George in his lecture, along with my own observations and experiences. In the course of his experiments with escapements and eventually inventing the coaxial, George Daniels investigated and analysed the qualities required for an escapement to be practical. He extensively discussed all these in this book here, The Practical Watch Escapement, which was first published in 1994, which is only, and it is the only complete text on the subject today. The search for new ways to improve the escapement is never-ending, and that is how it should be. However, I can't understand why the basic requirements of a good escapement are still not being followed today. In this talk, I am going to give examples of fundamental issues that George encountered in developing his escapements, add some observations of my own from over the years, and tell you a bit about my own journey of refining the coaxial escapement and the mechanism which drives it. So the first area to discuss are frictional rest escapements. So what is a frictional rest escapement? Well, where's my pointer? On the left we have the verge escapement, and on the right, the cylinder escapement. So basically, a frictional rest escapement is an escapement where the escape wheel, after giving impulse, is locked on some part of the balance axis, reducing its free movement. So in order to describe that, I will just demonstrate with the cylinder. Is that working? Yep. Okay. Now I'll just warn you, my drawing skills are very basic. I have a 5.5-year-old daughter who is now a better drawer than I am. So if you can just bear with me. But basically, a cylinder escapement, we have a circle. This is basically the cylinder of the stuff. This is a center line, or a center point where the balance pivot will be. And this is a center of our escape wheel. And coming out, we will have a tooth which basically rests upon the wall, the outside wall of the cylinder. So this balance wheel is turning clockwise and anti-clockwise for every vibration. And as the balance wheel turns clockwise, eventually this tooth will drop through the gap here and it'll end up inside the cylinder. So what we have is a tooth lying inside the cylinder, and it is this issue, or this is really what frictional rest is about, because at all times the escape wheel is trying to turn in a clockwise direction, and therefore it's applying pressure onto the cylinder or the stuff at these points. And it is this sort of pressure, this applied pressure here at all times, which restricts the free movement of the balance. And this is this is a real issue with the frictional rest. It doesn't allow the balance wheel to make its uninhibited free movement. So even though the virgin cylinder escapements have been consigned to the history books, there are two interesting features found in these two escapements here. And these are the way in which the power is delivered. And we can learn from this. In the cylinder escapement, the power is delivered through a sliding action. So basically, just a slide, and as it slides, it imparts power. Whereas in the verge, the power is delivered through a pushing action. And this is a fundamental difference between the two. However, I'll be discussing this later on in my presentation. So detached. What is detached? Well, a definition of a detached escapement is when the escape wheel is locked free of the balance axis by an additional component which is in contact with a balance only during the escaping angle and sometimes for less than the whole of this angle. It's getting confusing, isn't it? But it goes on to say that the balance is free to vibrate in its natural period during the supplementary arc. So I'll just do another quick sketch. So a good... Is that working? Is that on still? Yep. A good example of a detached escapement is a detent escapement, which is this one here. Highly detached, highly accurate. And if we have the center of the balance wheel here, you can see that over there, impulse jewel. And then coming down here, we have the detent with its screw there. On the detent, we have a locking jewel here. And then here we have an escape wheel center. We have teeth here. Now, when the escape wheel is locked, we have a tooth resting here on this locking jewel. And what this means is that when this escape wheel, which is trying to turn in this direction, is locked here, when it's delivered its impulse through this jewel, this balance is now free to make its rotation. And the reason is because we have clearance here and here, because of this locking here. So this is a good example of a detached escapement. And so a detached escapement is a quality which all precision timekeepers must possess, particularly if you want it to keep time. The finest of the detached escapements is the detent. Due to it being highly detached. Its one drawback, however, is that it's only suitable for life as a static timekeeper. And this is because impulse is only delivered in one of the two vibrations. So in conclusion, a good detached escapement will allow its balance to swing through its arc with minimal interference. The smaller the interference or escaping angle, the more opportunity the balance will have in a consistent arc of swing and therefore rate of timekeeping. So I better just clear up the sort of areas to do with angles and so on. So with the so a standard sort of arc of swing of a balance. Let's say if we choose a balance which is rotating at has a total vibration of 270 degrees. So basically, during the impulsing of a balance, when energy is delivered through to the balance, we have what's called an escaping angle. And that escaping angle is, in this instance, 40 degrees. We have an unlocking angle, where the escapement is unlocked, the escapement is unlocked to deliver the power, and that's 6 degrees. And then we have what's called a supplementary arc. And so we have 112 degrees of swing after each vibration. And it's this free vibration, this free sort of swing or supplementary arc, which is key in the accuracy of a precision timekeeper. So the total arc of all this, from here round to here, is 270 degrees. This area here, the balance doesn't swing into that area, so this is a swing back and forth like this. So this is key. So a real precision timekeeper, or if you're designing a precision timekeeper, what you want is the escape angle to be as small as possible. You want the interference of the escape wheel delivering its power to be minimum angle possible. Likewise, you want the unlocking angle to be as small as possible. And by doing that, what it enables you to do is have a nice, large, supplementary arc, which is really where the timekeeping is achieved. That's what you want, a nice, free sort of swing of the balance. So the next area I'll be talking about is our fast beat watches. So over the past 250 years of use, the frequency of the lever escapement has steadily increased from a generally accepted 18,000 vibrations per hour to 36,000 vibrations per hour. This is twice the rate. Now, why is this? Well, one of the difficulties in mass producing watches which contain the lever escapement is that the condition of the oil which lubricates it will vary dependent upon the climatic conditions of the country to which the watch is exported to. Another concern that watchmakers have is how long will that watch have to sit in stock for? What the technicians discovered is that by increasing the number of ticks per second had the effect of masking the variable conditions of the oil on the escapements, and this in turn averaged out this fluctuating rate. So for a 1 second, let's choose a 1 second period of time where we have 8 ticks per second. So we have 1, 2, 3, 4, 5, 6, 7. So let's say this is a trace of a watch after it has just been serviced and lubricated. And you note that all the ticks are nicely spaced, nicely sort of level and so on. But sometimes a few months after that, or as the watch gets older, the oil condition deteriorates. What we find is that we'll have the positioning of these ticks varies. And so what the technicians found was that by fitting more ticks into the second, what it actually did was averaged out the accuracy. So you had more of a consistent rate of timekeeping. So that was the advantage to a fast beat wristwatch movement. So most watches today beat at 21,600 or 28,800 vibrations per hour, giving 6 or 8 beats per second. But I would advocate that the aim of any watchmaker should be to create a watch which performs at around 18,000 vibrations per hour or 5 ticks per second. My thinking behind this is that for a fast beat watch to function, the design of the mechanism behind the escapement must change in order to provide the extra power to drive it. I would propose that this is not a good direction for a watchmaker to go, because this will only shorten the service interval and ultimately increase the running cost of owning the watch for its owner. A renowned heart surgeon recently said to me that small creatures generally have faster heart rates. Animals with faster heart rates have a shorter lifespan. Excuse me. I believe that the same correlation can be made with the fast beat watches, and we should take lesson from the natural world. And so to conclude, you should not increase the heart rate or vibrations per hour of a watch in order to hide the inefficiencies of a poor escapement design. Excuse me. I've not moved my slide on. There you are, that's what you'd be missing. So yes, that's a fast beat escape wheel, 20 teeth usually on there, but I'll tell you a little bit more about that later on as well. So impulse. Now this was not covered in George's 1990 presentation, and over the years I've become increasingly aware of the importance of delivery of impulse. And when I'm discussing impulse, what I'm really talking about is the clarity or the quality of impulse. And this I'm going to cover in a couple of sections. The first is delivery of smooth power to the escapement, while a second section is delivery of smooth power through the escapement to the oscillator or balance. If the impulse is delivered vaguely or sporadically, then you will not achieve a good rate of timekeeping. And so any impulse which is hindered by an applied lubricant or transmission of power will be open to vagaries in its ability to deliver good, clean and consistent impulse. And so let's first discuss the poor transmission of power to the escapement. So Breguet's natural escapement is a very good example of a poor transmitter of power through to the escapement. Why? Well, it's because of these two gears here. These two gears, which are linked together at a close ratio of obviously 1 to 1, and due to their large diameters, which at their rolling point of contact can act as large disc brakes on the power delivery. Because of that large diameter of these two closely mating gears, you can only ever achieve a theoretical rolling action between both sets of teeth. Why is this? Well, it is because for the wheels to rotate, they need freedom within their pivot holes. And it is this freedom which will allow the wheels to move past their theoretical rolling point, which will create interference and, in turn, fluctuating power delivery. Another issue to consider when using large diameter and close ratio gears is tooth surface contamination. And here is an example of where I've seen this occur on the slimline coaxial escapement. And it is where these two sets of teeth mesh together. So I began working on this escapement in 1998, and it became apparent fairly early on that these closely ratioed gears could cause issues, particularly if the surfaces were not scrupulously clean, but also if the surfaces were too clean. I also experienced tooth surface breakdown, which I put down to the fact that the true rolling action could never be achieved. And what I witnessed was a deposit build-up where the two gears ratios vied for settlement and created interference, resulting in a deposit build-up which caused the gears to stagger, or on some occasions to lock. So how do we reduce the risk of this interference? Well, in gearing, which requires freedoms for their smooth running, we can never completely remove this error, but as a watchmaker, it is my duty to minimise the error. And by using a traditional large gear driving a very small pinion, the effect of this varying depth of engagement between the two mating gears will be greatly reduced. This is because of the increased dominance of the larger driver over that of the smaller pinion. So two ratio gears, 1 to 1. So basically, two similar diameter wheels, and basically you have two lever actions which basically equal each other out. And because these wheels are a large diameter and lower down in the train where the power is starved, because of these large diameters, suddenly this issue of smooth transmission becomes more and more apparent. So the way around it is simply to use a traditional setup where you have a large driver turning a very small pinion. And it's a simple sort of lever action. Basically, we have the dominant gear that masks all the inefficiencies and weaknesses of the smaller gear. And that's really the way to create a nice, smooth running train of wheels. So in conclusion, if you are looking for a smooth transfer of power through to the escapement, then I would advocate not using close ratio gears in any part of the going train of a watch. Instead, use only traditional ratios, such as 7 to 1 and upwards. How do I start this, Nick? Just click again. Oh, sorry, Nick. Yes, sorry. Sorry. Thank you. Thank you. So just before I move on, here is a video of the extra flat coaxial escapement in action. This was made and fitted into a caliber 17170 movement by Patek Philippe in 1980. And you can see this very close ratio setup. It's actually a 2.5 to 1 ratio here. And you can see how possibly this is susceptible to stoppage and issues with surface of the mating gears becoming contaminated, and it's not a good idea, basically. Especially lower down in the train, when you're getting close to the escapement and the balance, when the power delivery is so critical, this sort of close ratio gears is in my mind a bit of a no-no. Thank you. So this next slide is concerning the Daniels double wheel escapement. This was fitted into the Space Traveller pocket watch, which recently sold at Sotheby's for a record £3.2 million. It's a fascinating escapement which heralded a major breakthrough for George Daniels in his quest to design an escapement which delivered impulse through a simple pushing action in both directions, and therefore remained unaffected by the deterioration of an applied lubricant. An excellent escapement, but its Achilles heel is that it requires an additional train of wheels and mainspring to drive the second escape wheel, and it is this overcomplication that has the potential to fail. So it's this extra escape wheel. Brilliant escapement, and he achieved what he wanted. He achieved radial impulse in both directions, which was key. Now, I'll just take this opportunity to say that in researching this presentation, I noticed that Wikipedia pages summarise the coaxial as follows. I have to go to Wikipedia to find out about it, you see. And I quote, it says, although a highly ingenious escapement design, the Daniels coaxial nevertheless still needs lubrication to the lever pallet pivots. I must say this is completely false statement. No oil is required on these pivots at all. It goes on to say, in addition, because of its geometry, the impulse wheel can only have a limited number of teeth. Thus it is necessary to have an extra wheel and pinion in the wheel train, the pivots of which will also need lubricating. Now, I would agree with the sentiment of this, but certainly in my experience, we do not need an extra train of wheels, and so we have avoided this completely. So we did a lot of work. I was determined when I set about designing the Series 2 that I was not going to have that extra set of wheels, and Andy Jones, one of my colleagues, who's a far better mathematician than I ever will be, came up with some very clever ratios to get around this issue. But what we did achieve is a very smooth running, high ratio gear train, and with a straightforward barrel, centre, third, fourth, and escape wheel, driving an 8-tooth escape wheel. So it is possible. Now, if anybody knows how to if anybody agrees with what I'm saying, and anybody who knows how to get into Wikipedia and correct this error, I'll be delighted if somebody could do it on my behalf. Thank you. So I've now concluded my section on smooth impulse being delivered to the escapement. Now we can look at how the escapement delivers smooth and constant impulse through to the oscillator being the balance wheel. So here we have the lever escapement and the Daniels coaxial escapement. Now, I touched on this earlier when I discussed the verge and the cylinder escapements. And you may remember that the cylinder is impulsed via a sliding action, sliding delivery of power, whereas the verge delivers its power through a pushing action. With these early forms of transmitting power, these early forms of transmitting power continue to this day in the form of the lever and the coaxial escapement. And here we have two sketches demonstrating the fundamental difference in power delivery between the lever and the coaxial escapement. So on the lever escapement, we basically have this tooth, which initially is locked here on this section here in red. And then as the escape wheel is released, as the lever moves, then this tooth slides down this long incline face, imparting this sliding action, delivering its power through this sliding action here. In the coaxial escapement, we have the tooth hitting the jewel here, and as it delivers its power from here through to here, through this straightforward pushing action, there is sliding action, but it's only this much sliding action, so it's minimal. And the fact that it's a pushing action, it doesn't really have an effect and doesn't really need lubrication. So one way I always use to describe the difference between how power is delivered between a coaxial and a lever, I will show you now. So, right. Believe it or not, those are door frames. So we have a hinge here, we have a door, and we have a door handle here. So when you all go home tonight, please practice this. And what I want you to do is to stand in front of the door with your hand like this. And first of all, stand with your hand just above the handle. And then basically just walk forward. And basically your hand will just slide down this portion of the door. And then you're through it. You've delivered your energy and got through the door to the other side. And then what you should do is stand by the hinge and put your hand here. And again, walk forward, keep walking forward until that door is fully open and you're out the other side. And basically what your hand will do is travel all the way down the length of this door as you impart this energy. And it is this sliding action here which is the drawback to the lever escapement. Now, for any impulse delivered through a sliding action, it will require lubrication in order for it to function. For an impulse delivered in a pushing action, this is not the case. And although I do use lubrication in the lubrication of my coaxial escapements, the lubrication is not there in order for the escapement to function. This is nothing new. If we look at the verge escapement and the cylinder escapement that we looked at earlier, the verge with its pushing impulse will always work without lubrication. And in servicing, you would never add oil to a verge watch. Whereas a cylinder and its sliding impulse delivery requires oil for it to function. It will not function without oil. And that's the same for the lever. As Breguet once said, "Give me a perfect oil and I will give you the perfect watch." He was partially correct in this statement, but I feel that what he should really have said is, there are no perfect oils for a watch, and therefore the watch must be redesigned. George Daniels realised this and designed a new and radical escapement by introducing pushing impulse in both vibrations, where its performance would not be affected by the application of a lubricant, which in turn advanced the life of the mechanical timekeeper. We have seen the difference between how sliding and pushing impulse occurs, but how does this play out in practice? Well, I hope this diagram helps to explain. So, the green here The green represents the angle in which the escape wheel is delivering its power through to the balance. So for a 4.5mm diameter escape wheel, the lever escapement spends 210 degrees of its rotation involved in the delivery of its power. For a 4.5mm diameter escape wheel of the coaxial, it spends an extra 45 degrees imparting its energy, which means that 255 degrees of its rotation is involved in the delivery of power through to the balance. And this is good. This is really good. This is a gain. And now what I found really fascinating when I was sort of working on this is that so when I calculated this, is that one revolution of a lever escape wheel, for one revolution of a lever escape wheel, it delivers 9mm of sliding action. And if you remember the lever jewel that we just saw before, we get a tooth that basically hits the jewel, slides down that jewel, and then down its inclined face. So it's basically multiplying this distance travelled by the 15 teeth that we have on the escape wheel of a coaxial escape, of a lever escapement. The reason for the red arc, well, that's basically the reason why the red arc is longer than the green arc. It's because of this long sliding action down these two straight faces. Of note is that should you add more teeth onto the escape wheel in order to create a fast beat watch, then you are further compromising the issue of the watch by increasing the amount of sliding action. And therefore the movement's power requirements will have to be increased in order to compensate. And so adding more teeth onto the escape wheel, in my view, is completely false logic. Now, if we look at the coaxial escapement, what is quite incredible is that even though there is a gained increase of power delivery, the amount of sliding action is only 1.1mm for one revolution of the escape wheel, and the rest of the impulse is delivered frictionless. It's just a simple frictionless pushing action. So for a lever, if we take that 9mm, divide it by the 220 degrees, we get 0.04. If we take the coaxial and we take the 1.1mm and divide that by the 255, we get 0.004. So if we take the 0.004, I can't bend down that far, divide that by we get 10. And that 10, for me, as a watchmaker, is very exciting, because that is basically 10 times, it indicates the efficiency of the coaxial over the lever escapement. It's 10 times more efficient. And this is brilliant. This is impressive stuff. So for a watchmaker, this is wonderful news, because these energy savings are something that the watchmaker can use in order to further enhance the life of the mechanical timekeeper. So what are the benefits to this energy saving? Well, it means that the vibrations per hour can be dropped down to 21,600, or my preference of 18,000 vibrations per hour, because this escapement is no longer reliant upon the use of a lubricant. and therefore does not have to hide the inefficiencies of the escapement and failure of the oil behind the high beat mechanism. We can go further and reduce the mainspring strength, which will be required to drive the watch. This reduced power will reduce the effort it takes in winding the watch, and also the effort that the mechanism has to endure in restraining all this power and then releasing it through its train of wheels, etc. The real gain here is that the watchmaker can then extend the service intervals of their watches and reduce the running costs to the owner. And so now, armed with the information and settled in the knowledge that the coaxial is a world-beating escapement, I began to look at how we can further improve its performance. So these are two of my single-wheel variants. The upper one there, is it working? Yep, the upper one there was the very first that I came up with the idea in 2010, and over the years it has now migrated into this sort of more lightweight variation. So in 2004 I began development work for my Series 2 wristwatch, and this was a big step for me because I wanted to use a coaxial, and although I had learnt a great deal whilst working with George on his Millennium series of watches, which housed the coaxial escapement, I was still unaware as to how to design and fit the escapement into a movement. And as you can imagine, the design phase was a very steep learning curve, but the result was the very first production watch in the world to have been designed to house this new escapement technology. So initially I used to make the coaxial wheels similar to, in the same process that George did. So basically, small pinion, and then we would mount onto this arbor the lower locking and impulse wheel, and then above that we would mount the second wheel. And this worked well for a period of time, but it was very, very difficult. Although the watches worked extremely well and we got a high degree of accuracy and so on, the issues that I encountered were the fact that it is virtually impossible to guarantee that the concentricity of these two sets of teeth here, of the two wheels, could be 100% concentric to each other. Not only did we have concentricity issues, but also there's a tooth there, believe it or not, and a tooth here. These two teeth, or two wheels, had to be angularly orientated to each other. And with a coaxial escapement, there is no room for error. It had to be bang on. And so this was a continual issue. So after several years of sort of head scratching, one of those sort of moments in the middle of the night when you wake up and think, oh, well, if I can make it out of one piece, maybe that'll solve the issues. So, So here we have the single wheel coaxial escapement, and basically it was made in one single operation, and it guaranteed that we had 100% accuracy, concentricity between these two sets of teeth, and also the angular distance between the two sets of teeth could be set at the point of manufacture. and that solved a huge amount of problems. So we achieved this, and immediately benefits could be seen in how the watch performed, but also the amount of time that it took in setting up of the escapement. The single wheel was born, but the benefits in performance that we were now enjoying, I felt could be exploited further. So the next stage was to redesign the lever to incorporate spring fixings to hold the jewels in place. And these were these sort of features here. So it's spring loaded, but it's all designed so that the jewels are always fixed at the correct angle and position. I then went further and lightened the escape wheel by removing some of this extra weight to create the lightweight single wheel. This time the improvements were dramatic, and it enabled me to reduce the strength of the mainspring with all the benefits associated with that. Interested by this link with weight to performance, I decided to look at reducing the scale of the escapement in the hope of finding more gains. Enthused with this new work holding techniques developed for the lightweight wheel, I realised that this could happen. A remanufacture of an existing dummy Series 2 movement took place, and the new smaller escapement was fitted. This time the savings in energy were off the scale, and a considerably weaker mainspring was sought to keep the escapement from knocking the banking. And here is a video of that movement. And with this piece, the escape wheel has been reduced from a diameter of 6mm down to 4.5mm. I'm afraid the clarity of the escape wheel there is not too good. I apologise for, but this has been really engaging work, and I now feel that we've entered into a new era of the development of the coaxial escapement. Due to the super efficiency of this escapement, I am beginning to understand that designing of new escapements should not all be about the escapement, but instead we should be considering the long-term effect on the running of the mechanism and savings in energy. This is really where the focus of watchmaking, in my view, should be. So armed with this experience, which has been steadily gained over the past 20 years, I set about redesigning my Series 2 mechanism to house this new and more efficient single-wheel coaxial escapement. This journey also caused me to rethink my production, and I've now created a small range of 4 pieces based on what I'm now calling my Mark II movement. The mechanism contains many technical changes which have all been as a direct result of the continual refinement of the coaxial escapement and my knowledge. And so this brings my presentation to a conclusion. But before I sign off, I will just summarise the qualities that a watchmaker should be looking to build into his or her watch in order to create a high precision, low energy demanding movement with an extended service interval. A watch providing minimum service cost and inconvenience to the owner. So beginning at the power end, we should look to have a single barrel, driving a train of gears which include a centre, third, fourth and escape wheel. Any more and it's an overcomplication. A gear train calculated to allow the balance to vibrate at no more than 18,000 vibrations per hour. A high ratio gearing of 7:1 and upwards to smooth out any inefficiencies found within the gears running, which would deliver smooth power direct to the escapement. And of course, highly detached balance. We need impulse delivered through to the balance in both the clockwise and anti-clockwise directions. And last but least, the power must be delivered to the balance through a simple pushing action, so as to minimise the effects on oil through climatic conditions and, of course, its own degeneration. And we'll leave you with this piece of advice, which in my view, or in my world, is very true. Thank you.
All right, anyone that has a question for Roger, please raise your hand and I'll bring the microphone to you. Come on, there's got to be some questions.
Don't push him, Nick.
Yes.
Thank you. Hello? It's working, right? Hey again, Roger. Thanks for the autograph. I took some nice notes and I have some wonderful questions.
Good.
So throughout the lecture, what I can gather is you've brought up, I'll say 2 or 3, let's call them 3 key points. One was in terms of the isochronism of the watch, the topology of the watch. And that was highlighted with the suitability of the lever versus, say, the detent escapement. Mm-hmm. Another one was with regards to the efficiency of a watch, and particularly in the last slide, you brought up the reduction in the mass of the wheel. So you lowered the moment of inertia of the wheel, and therefore you could use less power. And that's the second point. And the third point was when we were looking at the escaping angles. And you demonstrated with the lever escapement that we had 9 millimeters of total slide for the lever versus the 1.1 millimeters of total slide with the coaxial for the same diameter of wheel. And that brings up an interesting point, because what you're getting at is in a limit, as in the smaller you can make that action, the less friction you have. What that actually is, it's actually a true impulse, mathematically speaking. So that 9 millimeters of slide, that's the total distance of the surface on the pallet fork.
The 9 millimeters is the... I can go back, can't I?
Yes.
Yes. So this is the impulse joule. So it's that distance here.
Right, for...
Times 15.
The number of teeth.
Yeah.
Correct. So what I think might be interesting is, as you reduce the amount of surface you're sliding upon, what you're actually approaching is tangential motion. Mm-hmm. So that's basically a circle, and you've got a nice line. Obviously, in the limit, then you'll have a point, which is a true impulse. It's just like a flick. So by getting closer to that tangential motion, you'll be able to achieve what you're looking for in terms of reducing that escape angle and then freeing up more. The problem with that is the locking angle, I think. So it's a pretty interesting development to see this action. The other thing I had a question about was for the... I'm not monopolizing everyone's time. Okay. There's a pretty simple relationship with the lever escapement in terms of the beats per hour, and that's something like the square root of the moment of, the square root of the spring stiffness of the balance spring, and the moment of inertia.
You've lost me now.
I was just wondering if you've developed a similar relationship between the parameters of the Daniels or your coaxial escapement in terms of the balance spring and the moment of inertia of the wheel, to relate the beats per minute that one could expect.
Yeah, no, I'm afraid not, no. I mean, you have to understand, my sort of world is, as mentioned before, I'm not very good at maths and things like that. I know how to make watches, but I have to sit down and physically make it, physically design it. So technical questions like that are beyond me.
Oh, my bad.
Basically, what I do is, you over the years, you build up an intuition. So when I did start working on the coaxial, when I first designed the Series 2, I had no idea what the power requirements for a coaxial would be. And I just hoped that the gear train that I'd designed, the diameter of the escape wheel, the size of the balance would work. And it did. but I think that was more luck than anything else.
Okay.
But as you can tell, it's been developed over the years. It's developed in the 10 years that it's been around, and this is why we are where we are today with it. So my watchmaking is basically try something, test it, see how it works, see how it performs, and that's always been my approach. And sorry not to be able to give you more of a
No problem.
definitive answer.
Okay.
Roger, I've got a quick question for you. I know we talked about this earlier today, but you showed the gear train for your Series 2. How are you achieving the 1:60 ratio between the center and fourth wheel with an 8-tooth escape wheel? It looks like you have some other type of motion work happening on the dial side.
Yeah, what we basically have here. Where's my clicker? So we'd have usual hour, cannon pinion and hour wheel, minute wheel to turn around the minute and hour hands here. But to drive the seconds, what we have is we have this extended third pinion, and then we have a wheel mounted on there, and then we have this floating pinion. So it's this gearing here which converts the ratio to 60-1 between the minute hand and the seconds. So this is just a floating pinion. We put a very weak spring underneath that just to take out the vibration that you would see were it not to be there. But really that idea is used quite frequently in the 30mm Amigas and so on. So very standard sort of practice.
Okay.
A quick question, are there hairspring issues involved here that are part of all this?
Excuse me. No, I don't. No, not as far as I'm aware. We use a standard sort of excuse me, flat balance spring, and works very efficiently. Yeah.
The amount of energy to get the 270-degree rotation, wouldn't the hairspring be weaker? You're pushing it less hard?
Again, no, that's a good one, isn't it? My world has been so involved in the coaxial that, it's interesting, yesterday when I was doing the class with HSNY, it's the first time I've touched a lever escapement in almost 20 years. And so I've lost touch with the lever. I don't really have that correlation or, view anymore. All I know is that what we're doing, we're gradually improving and lightening everything. And I know I can base that on the mainspring strength, which we now use in the watch. It's a substantial watch, and yet we have a relatively light mainspring in there. So I suppose to answer your question, in theory, the balance spring will also be equally light as well.
I just want to say it was a wonderful presentation. And I have maybe about 3 questions. How do you feel about angling the escapement, anything in reference to that about accuracy? And I'm sure you're familiar with a couple watch houses doing that. What did you think about that?
Angling what? Sorry.
Just angling the escapement or the tourbillon, how do you feel about that? I mean, I didn't really see it in the... Correct.
Yeah,
like
yeah.
Grubel 4C.
Yeah. Well, that's it's a very logical thing to do, actually. Because with the best will in the world, to get a watch to keep time in the flat, where its pivot is just down, when it's on edge, it'll keep very different time because of the extra friction and so on. Excuse me. So angling it at 30 degrees is a good idea, but it takes up space. That's the issue. Now, what George did, which was interesting. Can everyone hear me?
Yes.
So he had an end stone. and his dual hull there with his pivot coming through of his balance staff. And what he did was he ground a off-centre sort of little cup onto the end of his end stone. And this had the effect that the end of this pivot always ran on this angle, this curve here. And so that equalised the edge positions from the vertical positions. So that was a brilliant way of getting around that issue without physically having to tilt your angle.
Wow.
And it maintained the slimness of the mechanism.
That's very interesting.
That was what George could do.
Wow, that's incredible. I'm actually reading his book right now, coincidentally on the escapement chapter. And also, you mentioned the, everything with your timekeeping, you became more accurate with your, I guess, your rendition of the coaxial.
Yes.
What was the, specifics in the, the seconds lost per year or whatnot, what I'm talking about?
Of the coaxial, the accuracy of this,
yes.
of the coaxial. Well, I mean, it can compete with any lever escapement. We believe it can be better, but the real gain is long term. So what you find with the lever escapements is as the oil deteriorates, 6 months, it can start to deteriorate. It can deteriorate gradually over a few years. But what we find with the coaxial is that because the escapement is not affected by the deterioration of the lubrication, you have a longer period of accuracy, so it's more stable long term. Right. So that's the real advantage. It's a long-term issue. That's right. What the coaxial was invented for, not for accuracy because it's as good as a lever.
Understood.
It's a long-term.
So that extra pallet stone or whatnot really reduces the friction and.
Yeah,
I'm sure it's deeper than that.
It's this pushing action.
Yeah. That's
a great advantage, and it's extended the service interval hugely. And I think even Amiga now, I read, again when I was researching the coaxial, I thought, well, better look at Amiga. And I'm sure I read somewhere that they are now having a 10-year service recommendation, wow. Which is pretty incredible.
That is impressive.
And that, to a huge business like Amiga, is a massive saving.
Yeah, wow.
Massive.
Thank you so very much.
Pleasure.
I appreciate it.
Pleasure.
Any other questions?
On the balance, now, because you're using less power on the mainspring, you obviously had to reduce the weight on the balance. With that reduction of the balance and the reduction of wear and tear, do you need to lubricate the end cap there? On the balance?
Oh, yeah, definitely,
You
very
still
much
do?
so. Oh, yes. It's so the balance dual hulls are still lubricated the same. We still lubricate the escapement as well, but it's just that it's not affected by that deterioration of the lubrication. I'm hoping. This series, the Mark II movement, which I've just developed, and. We're now in production with those watches, and the 4.5mm escapements we're now making those, and we're now at the next stage of development. So we've got the smaller escapement, the efficiency of the escapement has improved, the ability for the balance wheel to do its job of timekeeping has now been improved, whereas before we were seeing the escapement at times could influence the balance. Now we've got the balance as king. And so that's going to be taken forward. So we're going to obviously get a few pieces working, and then we can start playing around with the geometry of the escapement. And my goal is that we will, at some point, be able to have a completely oilless coaxial escapement. That's what I want. Whether we'll achieve it, who knows. But we can do a lot of work with adjusting the angles of the jewels, particularly with the draw. In theory, because the escapement's now lighter, smaller, in theory I should be able to back off the draw of the jewels, and I should be able to gain an extra 30 to 40 degrees of amplitude by doing that. And who knows, hopefully we can spring again. All the time you're looking at this obsessive approach just to sort of really try and drill down on perfecting this incredible escapement.
So the escape wheel is lubricated then? in this case?
Yeah. We always have done, and we had to do it. This goes back to the chronometer escapements, marine chronometers. You had to lubricate those, because if you didn't, what you would have is the tooth would hit the jewel, that locking jewel that I described earlier on, and that constant hitting. You'd get a build-up of deposit. You get this surface breakdown, and sometimes if you lubricate it, it just stops that, it prevents it. And particularly with cleaning methods, the modern cleaning methods, they strip the materials and the jewels, the steel, completely of any sort of lubrication, any sort of moisture, and you get a very dry surface. And I remember in the Millennium project that I worked with George, at first we used to run the escapements dry, and literally within 10 days you'd get a little red oxide build-up where the steel escape wheel would hit the jewel. As soon as we put a drop of oil on, it would just dissipate that. And that's down to modern cleaning sort of methods. And also fast beat, very hard on the escapement.
On the escapement itself, though, the material you're using on the escapement, the metal itself, for the coaxial, that's hitting the jewel, is that a softer metal or a much tougher metal, metallurgically speaking?
Softer.
Yeah, it would be, because you don't want a hard, it's like carbide hitting glass.
Yes, exactly, yeah.
Thank you.
Yeah, thank you.
Hi, mine's just a very practical question about your escapement. Can we get a top view of your escapement instead of a side view?
I don't have a top view.
Oh,
well,
yes you do.
there's a side view. Oh, sorry, sorry. I'm glad you know more about this than I do.
No.
It's this way, isn't it?
Perfect. Great.
Single. There, yeah.
How do you, the escape wheel must be extremely polished. Is that something you do with a file? And how do you know that you filed flat?
It's
very practical.
Yeah. It's very difficult. The tips of these teeth, I think it's about 0.015 of a millimetre, so you can't really polish that.
What do you do?
We allow the escapement to polish it.
No.
Yeah. So after a few weeks, it beats this sort of beating, and it hardens the tip of the tooth.
That's why you're using a saw. Because I was okay, fine. Because my other question was, if there's a physical reaction going on between the tooth and the wheel, wouldn't you change the amalgam of the material that you use for the escape wheel?
Yeah.
But no, that's extremely cool. So when we talk about lock here, the shorter the lock, the more power that you have to the escapement, yes?
That's right, yeah. Shorter the lock, as in...
Well, I'm not talking about impulse. I'm talking about when I only know for escapement. I apologize.
No. So when the tooth is locked on the jewel.
Yeah, when the tooth is locked on the jewel, you want to do you want to shorten the lock as much as possible?
Yeah, we do. You have to have draw in this. So yes, there is so draw has to be overcome.
Okay.
So that's what I'm looking at next, is can we reduce this angle of draw?
Absolutely. Sounds like fun.
It is, yeah. Okay,
Okay, next. Thank you.
Thank you. Thank you very much. Earlier you mentioned that the escapement itself is roughly 10 times more efficient than a lever. And I wonder if the mainsprings that you found deliver 1/10 the torque.
That's one of those technical questions again, isn't it? Yeah, I couldn't tell you. We just have a stock of springs, and if they watch over banks, we just go and find a weaker spring. And as I said before, my sort of world is very practical, and practical experiences, and you just try things out. So sorry, I can't help you with all that.
Did that pay off in power reserve? What's the power reserve of the Mark II?
So the power reserve is, off the top of my head, just over 48 hours.
Thank you.
Thank you. But that could change as well. We're still playing around with springs, canister sizes, and so on. So,
I wanted to ask a more general question about Roger Smith, the brand, I guess.
okay.
Do you intend to make your watches, more available, higher production in the future, or do you really, is the limitation to production because of the team and the complexity? How do you see the brand? Obviously, there's so much enthusiasm for you as a person, the watches you make, and the team, but will it always be such a kind of a limited watch?
Well, certainly for the foreseeable future. I mean, I've got sort of ambitions that I want to achieve, and we're currently building new workshops, and in theory they'll be ready in the middle of the new year, January, in the middle of January, sorry. And so yes, with the increased space, that will enable me to take on extra watchmakers. At the moment we've got, there's 8 in the business, 7 of us physically making watches and just making 10 pieces a year. So the idea is to add to that team, buy some extra equipment, but also I have in my mind, I have a body of work that I want to create. We're up to Series 4 now. Series 5 is up here, ready to get down on paper as soon as the Series 4 is completed. So the next sort of 10 years will be creating this body of work, building up a very good team of watchmakers where we have a real depth of knowledge within the team, and hopefully a permanent knowledge. In the past, we've always been susceptible to very good people joining us, and then for whatever reason, the Alaman is not always suited to everyone. They leave, and then we're back to square one again. So we're constantly adapting and changing our training methods and so on to cope with that. So training more local people, still bringing people in from outside to bring valuable knowledge, but try and keep a core base of knowledge on the Isle of Man, and then see where we are in 10 years' time with this sort of what I envisage to be 8 series, 8 pieces in the collection. Still making very small numbers. I'm not prepared to change that at this point. It's all I've ever done. People have sort of talked about, or suggested increasing numbers, but I know how to make 10 watches a year very well. And I want to go to bed and sleep at night. So for the moment, that's good. That's good. Suits me.
All right. Thank you, everyone. Let's have we have time for one more question. Let's have Melody can ask a question. One more.
It's all down to you now.
Oh dear. No. I saw the on the YouTube with George giving his talk, and he was there was a part that he did that was that was inspired by the motor car clutch. So I was wondering what other, because he was inspired by cars because he was at cars and stuff. So what about you? Is there somewhat like other industry or something that inspires you that would you put in the watch?
Not at the moment, I'm afraid. Sorry to disappoint. No, but I mean, it was interesting, that clutch mechanism from the that he first tried in the Space Traveller. Incredible. But interestingly, I don't know if you'll all know about Derek Pratt, who is a watchmaker and was a good friend of George and helped George at times with his quest to interest the Swiss watch industry in his coaxial escapement. And Derek Pratt was a very keen car enthusiast, and his great interest was the rotary engine. And he employed the rotary cam into his remontoire mechanisms. And it's interesting, the crossover. But I have an old Mini, so there's nothing too exciting in there. Thank you.
Roger, just one quick question. I'm surprised no one's brought this up. You closed with a quote from Da Vinci, which got me to think about the Da Vinci Code. And it strikes me that the Manx triskelion looks a lot like a three-tooth escape wheel.
Ah,
Is there some sort of like cabal or watchmakers society here?
well, if there was, I couldn't tell you.
Okay.
All right, thank you, everyone. Let's give Roger another hand. Great job. Good to see you, Roger. Fine, right here. Okay, so just before we conclude for tonight, Roger will be available for questions and photographs and selfies and autographs afterwards. And we'll try and be as British as possible. Please queue up in an orderly fashion to speak with Roger. And this is the last meeting of the year, and we'll see you all back here next month, Tuesday, January 9th, with Peter Speakmer in. Good night, everyone.